Okay, let's take a look at some of the examples in Chapter 3 and go over them. So as you're watching this video, please go ahead and pause the video, read the example, and then let's solve it together. As I am solving it, you have to have a pen and paper and solve it with me at the same time, okay? So go ahead and pause the video, read the example, read the problem, read it, and write down what you have on the corner, all right? And then let's solve it together. All right. So let me resize this a little bit, making it a little bit smaller. Maybe this, yeah, that's good. Okay, so what we have here is we have a neighborhood zip line that's set up from the large 3 to the ground. So the zip line makes an angle of theta of 18 degrees. So somebody came and measured that angle for us, and it says, oh, it's 18 degrees. Okay, so this angle right there is 18. So this angle is 18 degrees. Okay. And the anchor of the zip line is 12 meters away from the base. So technically what it's telling us is that this is 12 meters. Okay. So what we have is that we have this to be 12 meters, and we have this angle being 18 degrees. Okay, now the question is, what is the height of the top of the zip line above the ground? Now we're looking for this variable, this x. Okay, so if you're looking at this, just by looking at this, you can kind of tell which angle is the angle of right angle. So this is the right angle, 90 degrees, correct? So I know that this is 90 degrees. Now, if you remember from Chapter 3, the video lectures on Chapter 3, the tan of theta is x, which is the opposite direction of 18, so which is x, and over the 12, okay, so which is right there, adjacent to 18. So now I can just substitute the numbers. Tan of 18 degrees, you should put it in the calculator. There's no way that you can precisely calculate this with your brain. X over 12. In other words, if you want to find x, then x is 12 times tan of 18 degrees, which is, if you put it in the calculator, it will be 3.9 meters. So it's about 4 meters above the ground, okay? Now, part B is asking what length of wire is needed to make the zip line. So now basically we know right now we're dealing, so part B, we are dealing with a problem that is asking us to find this, which is our x now. So I have 12 here, I have 3.9 there, and this is the right angle. X squared is 3.9 squared plus 12 squared. So Pythagorean theory, that's what it is, right? And so x is then square root of 3.9 to the power of 2 plus 12 to the power of 2. If you do that, the final answer, and put it in the calculator, it will be 13 meters. So you need a wire of 13 meters to do this. Okay. Okay, let's take a look at example 3.5 or 3-5. It is a very important example, very, 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 very important example. So I can emphasize this more. I am going to highlight it because it is important. This example is like a base for us at this point. So what we have is a treasure hunt. So what are the magnitude D? So this D is this vector here. And direction, angle theta of the net displacement for a treasure hunt illustrated in the figure. All right, so what we have is a kind of a 3 vectors, A, B, and C in different directions, but the net vector, if you add them up, okay, you'll end up with D. We want to know the magnitude of D. We want to know the direction of D. Now, if it were just 2 vectors, okay, you know what you need to do for 2 vectors. You are using Pythagorean theory, right? So that's what you do with 2 vectors if they are having a right angle. If they don't, then you know what you need to do. If you don't, please go and watch the video lectures. Now, in this case, we have 3 vectors. We have 3.75 meters to the y, 2.25 to the x, and we have 3 meters and 45 degrees below the level. So this is what we're dealing with. Now, how do we solve the problem? In this case, okay, you need to break each vector to its components. One more time, you need to break each vectors to its components along x direction and along y direction. Let me get this a little bit smaller. Okay, so what we have here is we have vector A being 3.75 along y direction. So if I want to write A, okay, I know A of x is 0. Okay, I know A of y is 3.75 meters. Okay, so this is vector A. All right, so we have that. The reason for being 0 along x direction because it just does not have any component along x whatsoever. It's along y. Whatever magnitude that is associated with vector A, which is 3.75, is along y. It does not have any component along x direction. If I want to write vector A, I would write it like this: 0 in x direction plus 3.75 in y direction, I hat and j hat. Okay? Or kind of writing it like this: A is 3.75 j hat. Okay, so this, if this guy in the box would speak, it would tell us that I am a vector along y direction with a magnitude of 3.75. It would also say that I do not have any component along x direction. Do you see any I in there? No. So it's always along y direction. Now, you can write the same thing for vector B, okay? You can write the same thing for vector B. Let's do that for vector B. For vector B, okay, we have B sub x being 2.25 meters, 2.25 meters, okay? And we have B sub y being 0. Vector B does not have any component along y direction. It just doesn't have any component along y. It's along x, right? Even though it is up, but it does not have any component along y, okay? If I want to write B then, I would write 2.25 I hat plus 0 j hat. Or I can just easily write it this way: B is 2.25 I hat. Okay. Now, let's take a look at vector C. It is right there. It is 3 meters as its length, and it is below 45 degrees. Okay, so vector C. Let's take a look. It is 3 meters long. Vector C is 3 meters, right? And it is 45 degrees. All right, 3 meters long. Its length is 3 meters, but it's 45 degrees below, right? So if you want to find the x component of vector C and y component of vector C, it's actually very easy, right? So if this will be its component along y, right, C of y, and this would be its component along x, C of x, okay? And remember, we can move vectors, we can displace vectors as long as we keep its direction and its magnitude, we can move them around. So I can move this vector C of y right there and bring it all the way to here. So kind of making a triangle like that. I have C of x here. I have C of y here because I just moved it, and this is my vector C, right? This is 45 degrees, and this is the right triangle with an angle of 90. Okay, so now we're looking to find C of x and C of y. So this C is also 3 meters. Okay, now C of x is, what is it? C cosine of 45, and C of y is C sine of 45. Okay, C is 3 meters. Cosine of 45 is this, square root of 2 over 2. C is 3 meters. Sine of 45 is square root of 2 over 2. Okay, so I am just going to keep them like this, and we can put them on the calculator later on. So now I can write vector C. I can write vector C being C equals C of x along I hat along x direction, and C of y in j hat or along y direction, which is C being square root of 2, C being 3 times square root of 2 over 2 I hat plus 3 times square root of 2 over 2 j hat. So that's my C. I break it down to its components because I want to work with components. Now I have A written down with its components. I have B written down with its components. I have C written down with its components. Once you break down everything to their components, you need to check the directions, okay? Once you do that, you need to check your directions. Now, if you're looking at this, A is along positive y direction, so I have a positive here. B is along positive direction, so I have a positive here, right there. C has been broken down to C of x along positive and C of y along negative. So what it means is that this proportion, this part of C along y direction as a sign of negative. That's what it means. Okay. So if I want to use, if I want to put the this number for cy, this is the original formula, but if I want to do that, I have to have a negative here. Okay. So C of xi, C of yj, kind of like that. Okay. Now, once you break down everything to its components, it is time to add them up without any problems. So D is D is A plus B plus C, which is A is 3.75 j hat, 3.75 j hat, plus B is 2.25 I hat, 2.25 I hat, plus C is 3 square root of 2 over 2 I hat minus, now I have the minus sign, right, because because of that guy, 3 square root of 2 over 2 j hat, right? So now that I have written down D like that, I have to add all the I hats, I have to add all the j hats. So what I have then is I will add these two terms, and I will add these two terms because they're both along the direction that I'm looking for. So what I have is 2.25 plus 3 square root of 2 over 2 I hat plus 3.75 minus 3 square root of 2 over 2 j hat direction. Okay, now, so I wrote D kind of like this. Is this familiar? Yes, it is exactly this guy. D of x along I hat plus D of y along j hat. And this is exactly the same format. Now you can technically, right now, you can technically say that this guy is my D of x, and this guy is my D of y. Okay, now if that's the case, you have D based on its components. You have D based on along x direction and along y direction. So if you do that, basically, let me try to, so that's D, vector D. Now you have it along x direction, D of x, and you have it along y direction, D of y. This is the angle that you're looking for. Okay, you're looking for its magnitude and its angle, right? The magnitude is super easy. It's a right triangle, right? With this angle is 90 degrees. This angle right there is 90 degrees. So the magnitude of D is just D of x to the power of 2, which is this guy to the power of 2, plus D of y to the power of 2, which is this guy to the power of 2. Put them in your calculator, make them to the power of 2, add them up, put them underneath the square root, and then that will give you the magnitude of vector D, how much you have to move to get to that point. If you want to find theta, then you know the tan of theta, right? Tan of theta is rise over run, right? So you have D of y over D of x, or the opposite. If you watch the video lectures, you know what I'm talking about. H of opposite over h of adjacent, so h of a. So in this case, h of opposite is dy, and h of adjacent is dx. You know their magnitudes, you know what number they are. Just put this in your calculator, you will get dy. Put this in your calculator, you will get dx. And then theta, the direction, is tan minus 1 dy over dx. So we found the direction and we found the magnitude of vector d. That was, by the way, a horrible example. It's just not, it's too much. And if you're looking at the solution, it's the same thing. So theta is tan minus 1, this ratio, and dy and dx is by the way, just like that. So we'll go to the next example then. Okay, very interesting example 3-11. That's also very important. So go ahead and pause the video, read the problem first, and write down things that you have. If you need to sketch something, do it, and then we'll solve this together, right? Okay, now, I know that you have, write down some stuff, but let's go over the problem together. You ride in a boat whose speed relative to water is 6.1 meters per second. So relative to water, the boat speed is 6.1 meters per second. The boat points at an angle of 25 degrees upstream on the river flowing at 1.4 meters per second. So I have a river flowing down with a speed of 1.4 meters, and then I am going with an angle of 25 degrees. So this is the angle that I'm dealing with right there. That's the angle, okay, 25 degrees, okay? And we are going with respect to the water a velocity of 6.1 meters per second in this direction, okay? 25 above. And the water is coming down 1.4 meters per second. So it's going down 1.4 meters per second. The question A, part A, is asking, what is the velocity of the boat relative to the ground? So the velocity of the boat relative to the ground. Okay, so the velocity of the boat relative to ground is velocity of the boat relative to water plus the velocity of the water relative to ground. How do I memorize this without making any mistake? See, this B is right there. This G, which is the ground, is right there. And I have in the middle, I have water. Okay, so that's how you split it. And they are all vector quantities, so I have to put a vector on top of one another because they're all vectors, okay? Now, when you're looking at this, velocity of the boat with respect to water is a vector with an angle of 25 degrees. So velocity of the boat with respect to water is 6.1 meters per second with an angle of 25, okay? Now, it has a x component, velocity of the boat with respect to the water in x, and velocity of the boat with respect to water in y direction, right? So it's a vector, it has a y component, it has a x component. Okay, now you do that, you can easily find both of them. You can easily find the the components. So you can write it like this. Velocity of the boat with respect to water is velocity of the boat with respect to water along x I hat plus velocity of the boat with respect to water y j hat, okay? So it has a x component, it has a y component, okay? Now, once you do that, you can write them based on their components. So velocity along the x direction is 6.1 cosine of 25 I hat plus 6.1 cosine, sine of, not cosine, I hat plus 6.1 sine of 25 j hat. So I broke it down to its components along x and y direction. So it has it along both directions, right? Now, so I broke down this guy, velocity of boat with respect to water. Now, velocity of water with respect to ground is just downward. So velocity of water with respect to ground has a 0 component along I direction or x direction, but it is 1.4 meters down. So it is negative 1.4 along j hat direction. What is this negative for? It means that it is to the negative direction of y. Okay, so now I have to add them up to find the velocity of the boat with respect to ground. It's super easy to do that. Velocity of the boat with respect to ground is if you add these two. So you have to add their x component, you have to add their y component. So it is 6.1 cosine of 25 plus 0 I hat plus 6.1 sine of 25 plus, or maybe minus, right? So there minus 1.4 along j hat direction. Okay. Once you do that, you can find the velocity of the boat with respect to ground. This is g. And if you do that, you will find this number. So 5.5 meters per second along x direction. So if you do that, 5.5 meters per second along I direction plus 1.2 meters per second in y, 1.2 meters per second in y direction. Okay, so kind of like that. Now, what the question was asking, what is the velocity of the boat relative to the ground? So we found it. That's what it is. 5.5 meters along x, 1.2 along y. Now, if you want to find the magnitude, since you have x and y, and you can just easily write down the magnitude of the boat with respect to ground is its x component to the power of 2 plus y component to the power of 2. Okay, and then put it in the calculator to see what you can get. Part B is asking, suppose that the speed of a boat relative to the water remains the same. So the boat relative to water was moving with 6.1 meters per second, right? And it's given right here. Suppose it stays the same, it doesn't accelerate, doesn't decelerate, nothing happens to it, super easy, right? So, but the direction of which the point is changed. So what angle is required for the boat to go straight across the river, that is for the boat to move perpendicular to the shore? So in other words, what angle do I have to point my boat at to go straight perpendicular to the shore, okay, or to the ground? In other words, since the water is moving down, so this is part B, all right, so this is part B. Since the water is moving down, all right, so water is moving down right there. What direction should I point my boat at? Okay, what angle should I have all right? In order for my final result to be a straight line going to the shore without being up or down. No up, no down. What angle should I have it to go straight? Because we have a velocity from water, right? That's always pointing down, so I have to be careful. In other words, all of the y components should cancel out. If there is no y component along y direction, if I don't have any component along y direction, okay, then that means my final vector, okay, the result is not along y, it's always along x. In other words, this has to be true. So 6.1, which was this velocity, right? It says it doesn't change, times sine of theta should be equal to the velocity of the water, which was 1.4, correct? So sine of theta then is 1.4 divided by 6.1, and then theta is sine minus 1.4, 6.1, right? So that's the sine, that's the theta. So that's the angle. Just put it in the calculator to see what you get. I think the book has calculated it already for us, and it says 13 degrees. So theta is 13 degrees. That's the angle that you need to go straight without any velocity along y direction. If you go to 25, for example, if you go to 25, then your result will have some sort of a velocity along y. And that's what happens here, right? Our result ended up having some sort of a velocity along y, right? That's the one that I'm talking about. In this case, if the theta was 13, then this velocity would have been 0 because it will cancel out. Okay? Okay, another very, very important piece of example here. I am going to highlight it because it is extremely important. I want you to spend time, solving this problem a couple times and kind of master it. Okay, so let's read the problem. Pause the video, read the problem, write down what you have right now. Okay, now that you're back, the Dragonfly is initially at a position of R1, 4.6 meters along X hat, 0.96 along Y hat, so along X and Y right there. And as shown in the sketch, so that's the position is right there. It has a X component, right? It has a X component along X direction right there, which is 4.6 meters, right? 4.6 meters. And it has a Y component, which is 0.96 meters. That's what it is. Okay, now as shown in the sketch, after 3 seconds, the Dragonfly is at the position of R final, or RF, of 0.52. So right now, the final position along X is 0.52, and along Y direction is 2.4. Okay, what was the Dragonfly average velocity during this this time? Very important, very important. I can't emphasize more. So velocity, average velocity, okay, we know it's a vector. So you either use a bar or average, you can use both, who cares? But you have to have a arrow to indicate that it is a vector quantity. It is the displacement. Now displacement, what we usually used to show was delta x or delta y, but it is the displacement at this point is along both x and y. See, the components have both changed. The component along x direction has changed, the component along y direction has changed, right? It was initially this, and now it is something else. Both has changed. So the displacement vector here is not only delta x, not only delta y, but somehow both of them. And the way that we show it is we show it with delta r, okay? Delta r over delta t. So delta t is just the time lapse, how much time it took it for this motion to happen. It happened in 3 seconds. So that's what it is. Delta r is r final, which is a vector, minus r initial, which is also a vector. It has x component, has y component, so it's a vector. Now, so if I want to write that down, it will be something like this. So 3 is here. R of final position, okay? It has a 0.52 I hat plus 2.4 j hat, or instead of I hat, you can use x hat, instead of j hat, you can use y hat, minus r initial r 4.6 I hat plus 0.96 j hat. Okay, if you do that, then your average velocity become, so take a look, 0.52 I hat minus 4.6 I hat. So you have to put everything together along x and y. So you have 0.52 minus 4.6 I hat plus j hat, you have 2.4. So 2.4 minus 0.96 along j hat divided by 3. Okay, so if you do that, put them in a calculator, calculate them quickly, divide them by 3, then you would end up having this. You would end up having this number, which is this number right there, which is minus 1.36 x hat, which I just use I hat to show it, plus 0.48 y hat, I use j hat to show it. Again, I hat and x hat are the same, j hat and y hat are the same. You can use different notations. I prefer this way. You can use x hat or y hat. It's up to you. Now, this is the average velocity for this Dragonfly to go from one point to another in 3 seconds, okay? If you want to find the magnitude of it, super easy. Find the magnitude. Every time that you broke apart a vector to its components, I emphasize, every time that you are breaking apart a vector to its components, you can just use the magnitude. You can just write the magnitude of it like this. X component to the power of 2 plus y component to the power of 2 under the square root. And boom, done. This is our average velocity, magnitude of average velocity. Let's take a look at this problem. This is also very important. Now we're dealing with, in this problem, a average acceleration. So without any further ado, let's take a look. We have a car traveling with the initial velocity of VI, negative 6.36 meters per second along x direction, plus 6.36 meters per second along y direction. X hat and y hat, you can use I hat or j hat, it's up to you, I don't care. 8 seconds later, after following the bend in the road, its final velocity is, V final is 15 meters per second along y direction. What are the magnitude and direction of its average acceleration during those 8 seconds? Okay, so average acceleration, A average, if you remember, was delta V over delta T. Delta V, change of a velocity. Velocity is a vector. The change of it is also a vector. So delta T is just 8 seconds right there. Boom. Delta V is V of final, which is a vector, minus V of initial, which is also a vector. Okay, so I just want to write it down. V of final is 15 meters per second along y direction. So 15 j hat or y hat, up to you. Okay, that's VF. VI is minus 6.36 meters per second I hat plus 6.36 meters per second j hat, right? So that's what the VI is. Okay, now over 8 divided by 8. So what I have is an A average being 15J minus 6.36J. So minus 6.36J, okay, plus, so minus times minus is plus, plus 6.36 I hat divided by 8. So you add up all the i's, you add up all the j's. What you're going to end up with is this 6.36 I hat plus 15 minus 6.36. 15 minus 6.36 j hat over 8. Okay. All right, so then what it means is that your A average, after you put them on the calculator, your A average is 0.795 meters per second square along I hat direction. So if you divide that 6.36 by 8, you'll get this. Plus 15 minus 6.36 over 8 is just 1.08 meters per second square along j hat direction. If you want to find its magnitude, A of average, magnitude of it, I put in 2 parallel lines to indicate that it is, I'm talking about a magnitude. If you want to find a magnitude, if you have broken apart the vector along x and y to its components, all you need to do is to put them under the square root. So x component plus y component to the power of 2, kind of like this. And that would be your A average magnitude. For direction, right? For direction, we use this. Y over x, right? So we have tan negative 1 of 1.08 over 0.79, and whatever it is, that will give you your direction. Okay, example 3-10, I am not going to solve it. I want you to solve it right now. If you're watching this video, go ahead and think about this problem. Use a pen and paper, write down everything that you have. You have to go to the book, figure 3-33. Go and check that figure and try to solve the problem. Spend time. This is a problem of relative speed. We solved a problem of a relative speed before, right there. Okay, 3-11 is a relative speed problem. And I extensively talk about the relative speed in Chapter 3, Part 3 video. So go ahead and check that out as well. If you have any questions, email me, and I'll talk to you guys soon. All right, bye.